So let me know when you would like me to start. Okay, shall I start now or are we waiting for a few more minutes?
Oh, like as we mentioned, like we already start turn 5, so let's like how to say, maybe not exactly turn 5, but we can start like turn 2 or turn 3, something like that, which is like we give some extra time for some person, like they say, oh, I know this like webinar, they always like a little bit late, so they don't, lost any information. Like, I mean, you prepare the talk very well, I'm pretty sure.
Mm-hmm. Sure, that's fine. Let's just give it another couple of minutes and we'll get started.
Just a couple minutes, like couple minutes later, we can start.
Yeah.
So Dr. Carrie Ramesh, maybe you can start the seminar.
Okay, thanks very much. Okay, hello everyone. I'm Kiran Ramesh and I'm a senior lecturer / associate professor at the University of Glasgow. I'd like to say thanks to IBiM for inviting me to deliver this seminar. My talk today is going to be on physics-based low-order modeling of unsteady external flows. And I'm going to be showing some work which has been done by some of my PhD students, Hugh Bird, who has recently graduated, Alfonso, who is going to graduate very soon in the next few months, and Mark Patrul, who is a first-year PhD student currently working with me. So first, a quick introduction to unsteady flows and unsteady aerodynamics. So very broadly, we can say that these flows result from time-dependent changes in the flow, which you can see here in the case of flow behind a bluff body or flow behind a stalled airfoil. In other cases, unsteady flows can also result because of changes in the position or shape of the body. For example, flapping flight, morphing wings, and so on. And broadly, we see these dominant features in unsteady flows. So we see trailing edge wakes, which have these von Karman streets and other similar structures. We see flow separation, where the flow pinches off from the airfoil at some point on the airfoil surface, resulting in stalled flow. And we also see leading edge vortex shedding, where we have a vortex that results from a shear layer being formed at the leading edge of the wing. So when it comes to modeling unsteady flows or studying unsteady flows, there are a number of approaches that have been pursued by various researchers. So I'm just going to talk about some of these approaches to provide some context to the work that we are doing in our group. So we have theoretical or analytical approaches. The pros of these methods are that they are very fast to implement and they improve our understanding of the flow physics. But these methods are limited by several assumptions like small amplitudes, attached flows, and so on. And they are not applicable outside of these assumptions. Experiments in CFD are very reliable. They improve our understanding in a broad range of flows, and usually they are useful to get past the assumptions that are imposed by theoretical methods. However, the limitations are that they are usually expensive or slow, and they can't really be used for real-time simulation and design. And although CFD is improving every day, it's still difficult to use it for real-time applications and so on. We also have a class of methods called semi-empirical methods, like the Leishman-Beddoes model and so on. And these are very fast and they've been used very successfully for simulation and design. However, these usually depend on empirical parameters and they don't provide too much insight into the flow physics because they're typically based on curve fits and empirical data. So in our group, the method that we follow is we use theoretical modeling and we try to eliminate the assumptions as far as possible. And beyond a point, when theoretical methods don't work anymore, we try to augment the theory with numerical methods to account for viscous effects or viscous phenomena. So we'll talk a little bit more about what exactly this means in the upcoming slides. Okay, so in the first part of this talk, I'm going to be presenting on modeling leading edge vortex dominated flows in 2D. So this is some of the work that was started and done during my PhD at North Carolina State University. The basis of the method that we use for modeling leading edge vortex flows is what is known as unsteady thin airfoil theory. So this is a time stepping method where at each time step we solve a certain problem. So here we can see this XYZ is the inertial frame that is fixed to the ground, and we have a body frame that moves along with the airfoil. And at each time step, we shed a discrete vortex into the wake. So here, just like in conventional thin airfoil theory, the airfoil vorticity is represented as a Fourier series. Now, we have the typical assumptions of potential flow, that the flow is inviscid and the flow is incompressible. The amplitudes and frequencies may be arbitrarily large. So here, the unknown at every time step is the vorticity distribution or the Fourier series on the airfoil. So here's a demonstration of how this method works. So what we are looking at here is a 45 degrees pitch ramp return motion. So over here, we have some experimental data for this case. So we can see that we have a airfoil starting off at 0 degrees angle of attack. It pitches all the way up to 45 degrees and stays there for a while and then comes back down to 0 degrees angle of attack. And let's look at the lift coefficient on the right. So we have results from experiment, we have results from CFD, and we have results from the unsteady thin airfoil theory that I just spoke about. So here, if we look at the theoretical results, we can see that in the first part of the motion, the theory actually does quite well during the upstroke when the wing is pitching up to 45 degrees. However, as soon as we have this vortex formation and detachment that is shown in these figures over here, the theoretical prediction starts over-predicting the actual experimental and CFD prediction. So in this case, we see that this is a case where we have a leading edge vortex present, and we see that the theory over-predicts the lift in the vortex-dominated region. So what we learn from this is that this unsteady thin airfoil theory is actually a useful tool, but it can't be used in regions where leading edge vortex detachment is present. So for that, we need to do something else. We need a better model, and we need to augment this unsteady thin airfoil theory with some numerical procedures. So in order to do this, we developed what is known as the LESP hypothesis. So LESP stands for leading edge suction parameter. And here the basic hypothesis is that the maximum suction that can be supported by the leading edge of an airfoil depends on the shape of the leading edge and on the Reynolds number. And what we say is that for every given airfoil and Reynolds number, there is a maximum LESP value or a maximum suction value which cannot be exceeded. And if it is exceeded, then flow separates from the leading edge. So when this maximum LESP is breached, leading edge vortex formation occurs. So flow separation starts and you get the start of vortex formation from the leading edge. So let's show a demonstration of how this works. So here we are considering 6 different motion kinematics, combinations of pitch and plunge where leading edge vortex formation occurs. So those are the 6 figures shown over here from experiments. And in these different cases are all at different amplitudes, different frequencies, and so on. So the leading edge vortex formation happens at different angles of attack. So here we've plotted the time at which the leading edge vortex formation happens against angle of attack. So the upper triangles stand for leading edge vortex formation on the upper surface of the airfoil, and the downward triangles stand for leading edge vortex formation on the lower surface of the airfoil. So here, looking at this figure, we can see that there's really no trend in terms of angle of attack. So depending on the kinematics and depending on the frequency, leading edge vortex formation may occur at any given time and at any given angle of attack. So there's no pattern over here. But if we plot the same data in terms of the LESP or the leading edge suction parameter, we see that vortex formation on the upper surface of the airfoil always happens at one particular critical value of this LESP, and leading edge vortex formation on the lower surface of the airfoil happens at the exact negative of the same value. So this LESP parameter can essentially be used to predict or to control leading edge vortex formation. And this is a method that is completely based on inviscid aerodynamic theory. So next we show a demonstration of how we can control leading edge vortex formation using this LESP parameter that we just demonstrated. So let's consider a pitch only ramp motion. So amplitude of 30 degrees. So we have an airfoil that pitches from 0 degrees up to 30 degrees at reduced frequency of 0.2. We are using an SD7003 airfoil and the Reynolds number is 20,000. So here, what we are going to try and do is to superimpose a plunge motion on this pitch motion so that certain requirements on leading edge vortex formation are met. So let's look at this first figure here. It shows angle of attack. So the black line shows the baseline pitch kinematics. We have the pitch kinematics going from 0 degrees up to 30 degrees angle of attack. And on the right, we have the LESP. And again, the solid black line shows the LESP for the baseline case. And we can see that the critical value is reached at around time equals 1, right? So for this baseline case, the leading edge vortex formation happens at time equals 1. Now, what we want to do is to add a plunge motion so that the leading edge vortex formation happens at time equals 0.5 instead of time equals 1. Or we want to impose, in a second case, a different plunge motion so that the leading edge vortex formation happens here at time equals 1.5 rather than 1 as in the baseline case. So using this LESP parameter in an inverse sense, we calculate these plunge kinematics that are shown in this figure. So what we are trying to do here is to add some plunge so that we trigger leading edge vortex formation at any given time that we want, or to delay leading edge vortex formation to any given time. So the baseline case, it happens at 1, and we are adding plunge kinematics so that we can either move it earlier to 0.5 or move it later to 1.5. So let's see how this works using CFD data. So we calculated this using the inviscid theory, and then we simulated it using CFD. So the first column here shows the baseline case. And here we can see that the leading edge vortex formation happens at time equals 1, as we saw. So this is when the maximum LESP is exceeded. So that's the first column. Now, in the second column, the plunge motion has been added. And here, just as we wanted to do, we are able to trigger the leading edge vortex formation at time equals 0.5. So by adding a suitable plunge motion, we are able to advance the leading edge vortex formation. And finally, the third column shows the case where we try to delay the leading edge vortex formation to time equals 1.5. So here we can see that until time equals 1, there is no vortex formation, and it only happens here at time equals 1.5, just as we've designed it. So this is how this parameter can be used to control leading edge vortex formation. Now, in addition to predicting and controlling leading edge vortex formation, we can also use this parameter to model vortex dominated flows. So here we've developed a discrete vortex method that is known as LDVM. So that stands for LESP modulated discrete vortex method. So we are using the LESP to manage leading edge vortex shedding in this discrete vortex method. So LESP is used to predict leading edge vortex shedding, just as we showed previously. And during the simulation, if at any time the LESP becomes greater than the critical value, then we start shedding these discrete vortices from the leading edge to simulate leading edge vortex formation. So here, discrete vortex elements are used to represent the separated flow. So let's look at a demonstration of this. So we have a flat plate pitching up to 90 degrees, and we are comparing the LDVM against CFD data. So looking at the lift and the drag, we can see that we are getting a very good approximation to CFD using this very simple discrete vortex model. And let's have a look at how the flow is modeled by our LOM or low order model. So here, the CFD, we see that the plate starts pitching up, and at time equals 1.5, we have the start of leading edge vortex formation, which is also predicted by our method. And then as time progresses, this vortex grows, and this is also accurately predicted by our method. And we can see that at maybe time equals 4, the vortex starts detaching from the airfoil surface, which is again accurately predicted by our method. So we can see that all the important coherent structures are predicted quite well by this very simple low order method. And here, the number of degrees of freedom in the CFD depends on the number of cells in the mesh. It might be, even for a low Reynolds number case, it might be a few 100,000, whereas we are able to simulate this using just less than 100 degrees of freedom or so, using these discrete vortex elements. So this simulation typically runs in maybe 2 or 3 seconds on a typical PC. So just to wrap up this discussion, the LDVM, it's a very general formulation. Because it doesn't use a grid, it can be used in various problems, and it can be coupled easily with other solvers. So it's very easy to do fluid structure interaction and so on, because we don't have a grid, which makes things complicated. And this method allows for quite large time steps, and it's computationally very cheap. The typical runtime is maybe 4 seconds or less. So this can be used for real-time simulation because of the very small runtime. It can be used for quick parametric studies, and it can be used for preliminary design and optimization. So if we have a very large parameter space, we can use this method to cover that parameter space, and then we can go in further and explore with high fidelity tools like CFD and experiments and so on. However, we do have some limitations. Trailing edge separation is not modeled. We are only looking at leading edge vortex formation in this method. And trailing edge separation is very important in problems like dynamic stall, which happens at low rates of motion. And also, it's a 2D method, and it's not applicable to finite wings. So in the next 2 parts of this talk, I'm going to be talking about methods aimed at addressing these 2 limitations. So in the second part, let's talk about unsteady lifting line theory, which is a way of extending these methods to 3D flows and for finite wings. So unsteady lifting line theory gives us an analytical solution for unsteady oscillating wings. So it's a way of taking the unsteady thin airfoil theory that I spoke about earlier to 3D and to finite wings. So again, here we have some assumptions and limitations. It's only for small amplitudes. It assumes a planar wake. It assumes no flow separation, and it assumes large aspect ratios. However, just as we showed earlier, we can use numerical methods to get past some of these limitations. And unsteady lifting line theory is basically an intermediate to 2D and 3D methods. So it's obtained by augmenting 2D models with corrections that are gathered from a simplified 3D model. So it involves some complex integrals, but these can all be pre-calculated. So the computational time is still very, very low. And just as an unsteady thin airfoil theory, we can get the solution here in terms of Fourier coefficients, which are very useful to predict and model leading edge vortex formation and so on. So I'll just show some quick results from unsteady lifting line theory here. So in our work that is published in this article shown here, we've developed or looked at 3 different models of ULLT. These are the complete ULLT, which has been published in the 80s by Sklavonis. And we've developed a simplified version of the ULLT. And we also have a pseudo-steady model of the ULLT where we assume that the flow is steady at every given time step. And here in the results that are shown, we are comparing against Euler CFD simulations. So this plot shows the results for an aspect ratio 8 wing, and this plot shows results for an aspect ratio 2 wing. So let's first look at aspect ratio 8. So here the CFD results are shown by the star symbols, and we have the 3 ULLTs, and we can see that all 3 of them compare quite well to CFD across the range of reduced frequencies. Now, many researchers use strip theory for 3D, and the strip theory is shown in black over here. So we can see that unsteady lifting line theory provides a very good improvement over strip theory, especially at low reduced frequencies. And let's look at the aspect ratio 2 wing. So technically, unsteady lifting line theory is not really valid for aspect ratio 2 wings. It's only valid for large aspect ratios. But here we can see that the PULLT is still giving us a very good prediction across the range of reduced frequencies, even for the aspect ratio 2 wing. And more importantly, we can see that this method is much better to use than strip theory, which is quite far away from the CFD results. So the takeaway from this is that unsteady lifting line theory is just as easy to use and implement as strip theory, and it provides much better results. So we've previously been looking at Euler CFD results or inviscid results. So now let's look at some URAN solutions at Reynolds number 10,000 for cases that also have some nonlinearities like leading edge vortex shedding. So here, we are looking at a 2D case, aspect ratio 6, aspect ratio 3, and aspect ratio 1. So let's see how this ULLT does for different aspect ratios. So the ULLT result is marked in the dark black line. And then we have CFD results for 3 different plunge amplitudes. So a very small plunge amplitude of 0.05, an intermediate amplitude of 0.5, and a high amplitude of 1. So let's first look at the flow visualization for these cases. So we can see that if we look at the flow, we have quite a large leading edge vortex structure that is being formed on the airfoil for all the different aspect ratios. And looking at the lift prediction, in 2D, we see that there's a significant nonlinearity that comes about because of the leading edge vortex shedding. So the ULLT agrees very well for the small amplitude case, but for the larger amplitudes, there's quite a bit of error. But as the aspect ratio decreases, it turns out that the nonlinearities or the leading edge vortex effects are damped by 3D effects. So really, we don't see too much of a difference between the 3 CFD results for the smaller aspect ratios. And we see that unsteady lifting line theory does a pretty good job of approximating the lift coefficient, even for cases where we have this complex nonlinearity and leading edge vortex shedding. So the takeaway here is that unsteady lifting line theory is a useful tool to get a first order result for these complex scenarios. And to account for these differences that we see over here, we can use some numerical methods, like for example, the discrete vortex method that I showed earlier, to account for the separated flow structures and so on. So until now, we've only looked at harmonic kinematics or sinusoidal kinematics. Let's now also look at some arbitrary ramp type kinematics. So unsteady lifting line theory is really only developed for harmonic kinematics, but we've developed a method to also be able to apply it to arbitrary motions. So what we do here is transform the time domain kinematics to the frequency domain. We perform a convolution, and then we return the results back to the time domain. So here again, we compare CFT for aspect ratio 4 wing against the method that we've developed, which is called UCOFT. And we also compare against strip theory. So we are looking at lift coefficient and pitching moment coefficient for this angle of attack history shown over here. So we can see that our method is very, very close to the CFT and provides a much better approximation than the strip theory, which is the line over here, which is quite far away from the CFT result. And same thing for the pitching moment. So unsteady lifting line theory is able to give us a very good approximation to the CFT results. So that is the work that describes how we are planning to do the low order modeling in 3D flows. So in the final part of this talk, part 3, I'm going to be talking about predicting arbitrary unsteady flow separation. So the models that I showed previously are only capable of predicting flow separation from the leading edge. They can only predict leading edge vortex formation. So the work here aims to extend that to be able to predict separation from any random location on the airfoil. So in order to do that, we are using the unsteady boundary layer equations. We are using the integral form of the unsteady boundary layer equations. We are using a specific form that has been developed by Matsushita and Akamatsu. So the equations here are not important. I've just put this up as a reference. So the details are available in these papers that are listed over here. So this integral version of the unsteady boundary layer equations are a hyperbolic system of equations. And in any hyperbolic system of equations, for example, equations of supersonic flows, it's possible to have discontinuities. And these discontinuities are indicated by the formation of shocks in the data. So in this case, the discontinuity or the shock arises because of flow separation. And this is what is known as the Van Dommelen singularity in the literature. So this is the singularity beyond which the unsteady boundary layer equations cannot be integrated any further because you have the occurrence of flow separation. So what we do is we define a quantity called C separation to identify the discontinuity and hence the boundary layer detachment. So this is basically a way of predicting flow separation from any random location on the airfoil or the wing surface. So I'll just show a demonstration of this. So here we are looking at a very simple test case, the flow past a stationary cylinder. So for a stationary cylinder, the inviscid solution is well known. So the inviscid solution is just sine x, where x is the coordinate of the cylinder. So here on the left, we have the displacement thickness as shown at different instants of time. And we have the shape parameter from the integral boundary layer equations shown on the right. So we can see that the displacement thickness initially starts off flat. And as time progresses, at the rear end of the cylinder, the displacement thickness starts growing. And eventually, we get this shock-like formation over here. So this vertical line in the displacement thickness, which is kind of like a shock, denotes that flow separation is about to happen. So when we get this kind of a shock, the equations become very stiff and it's not possible to integrate the equations beyond this point. So this is actually when flow separation occurs. So we can use this to predict the occurrence of flow separation. So let's look at this in terms of the separation criterion that I described earlier. So initially, the separation criterion is quite flat because it's the derivative of the displacement thickness. But when the displacement thickness develops that shock-like singularity, we get this big spike in the separation indicator. So when this spike crosses this critical value over here, that gives us a signal that flow separation has occurred. So this is how we have a method for predicting general flow separation. So here we are comparing the time and location of the singularity against published data, and we can see that we are able to predict it within 3% of error. So the case that I showed earlier was a very simple test case for a cylinder. So now let's look at how to apply it for an airfoil. For an airfoil, we need to look at viscous inviscid interaction. So we have the inviscid solution on the airfoil, which interacts with the viscous boundary layer solution. Now, as I just mentioned, the boundary layer solution can't proceed beyond the singularity. So that's the point at which the equations stop working. It's not possible to integrate beyond that. So beyond that, it's important to model the interaction. The changes in the external velocity distribution must be modeled, and interaction with the external potential flow solution is required. So here, the inviscid method that we're using is the unsteady airfoil theory that we discussed earlier. And there are a number of methods of modeling this viscous inviscid interaction. So for example, an Xfoil, which is a viscous inviscid interaction software for steady flows, it's done through transpiration velocity. But here we are doing it through displacement thickness by changing the effective shape of the airfoil, which I'll demonstrate in just a second. So let's look at how this method works. So here, this plot shows the edge velocity on the airfoil for a NACA 12 at 0 angle of attack. So at time close to 0, we can see that the edge velocity on the airfoil has a sharp gradient near the trailing edge, which is as expected because it's an inviscid solution initially. But as time progresses, because of the viscous inviscid interaction and because of the effect of the boundary layer, this gradient gets shallowed out. And the displacement thickness is shown here. So initially we start off with the Blasius basic displacement thickness. And as time progresses, we initially seem to be getting a kind of a shock, but it's not really a discontinuity, and we don't really have flow separation in this case because it's only a NACA 12 at 0 angle of attack. So at time equals 2, we get this displacement thickness over here, shown by the blue line, which is very close to the steady solution predicted by Xfoil. So here what we are doing is we are running an unsteady simulation for a NACA 12 airfoil at 0 angle of attack. And we can see that after some time, it basically converges to the steady solution that is given by Xfoil. So that's the pink dashed line. And here, if we look at the separation indicator, we can see that we never really exceed the critical value. So that's because a NACA 12 airfoil at 0 angle of attack doesn't really have any separation. So it has flow reversal. So we do have zero skin friction at x by c equals 0.8, but we don't really have flow separation or flow detachment in this case. So these are all things that we're able to model with this method. So here's another demonstration of how exactly this method works. Sorry. So here we are comparing against unsteady RANS, which was performed in our group in OpenFOAM. So we are looking at a NACA 12 airfoil again at 0 angle of attack, and we are looking at Reynolds number 10,000, 5,000, and 1,000. So we have time equals 0.5, time equals 1, time equals 2, and time equals 5. So initially, our results are not very close to the CFT, and the reason for that is because the initial conditions in our method and in the CFT are quite different. But as time progresses, we can see that the displacement thickness predicted by our method is very close to that which is predicted by the CFT. And on the right, we see how exactly our method works. So as I mentioned earlier, the way we model the viscous inviscid interaction is by changing the shape of the airfoil. So we have the NACA 12 airfoil shape initially, and then because of the effect of the boundary layer, because of displacement thickness, the shape of the airfoil gets modified to what we see over here. So we can see that the effect of the boundary layer is much more significant at lower Reynolds numbers, which is something that all of us are familiar with, right? So at a lower Reynolds numbers, we have a thicker boundary layer, So the shape of the airfoil is modified more significantly, as we can see here. So here are the conclusions. So, sorry. Again, the integral boundary layer method is a very inexpensive method of approximating boundary layer phenomena, such as boundary layer thickening and boundary layer separation. And we are modeling viscous-inviscid interaction by changing the effective shape of the airfoil. And in this research, we are making a distinction between flow separation, which is indicated by the singularity, and between boundary layer thickening and reversed flow. So in these cases, we do have boundary layer thickening and reversed flow, but we don't really have flow separation, which is the detachment of a shear layer from the airfoil surface. So we haven't yet reached a stage where we can model separated flows. So that is something that we are still working on. And the plan is that once we detect flow separation that occurs, which we saw in the cylinder case, for example, we must model it by shedding discrete vortices, which will be similar to the leading edge vortex modeling that I showed earlier, by shedding discrete vortices from the separation point. So these are the conclusions. So the work that I've shown here shows, spoke about some inviscid methods that we can use to build more complex SON. So in 2D, we use unsteady airfoil theory on a base, as a base, and we use some numerical methods to account for effects of viscosity and so on. And similarly, in 3D, we can use unsteady lifting line theory. So we are using viscous-inviscid interaction methods to dynamically predict and model arbitrary separation. And these methods give us a way to model unsteady external flow with a very limited number of states. So in all these cases and examples that I showed earlier, the number of states is never more than a few hundred. So it's a very compact system in terms of the number of states, which in turn is very promising for machine learning applications and so on. Because we only have a few number of states, we can pose it as a state space problem and use the available machine learning methods that are available in the literature, which you can use to improve the results and to add higher order corrections. Okay, so that's my talk. Thanks very much. And if you have any questions, I'd be happy to take them.
Yeah, thanks for Dr. Ramesh to give us this highly delivered talk. So apparently the talk is highly organized and very logical. So if you have any questions regarding Dr. Ramesh's low order models, you can just open your mic and ask questions, or you can left your question in the chat. If no one has a question, so I would like to ask a question to initiate. So Dr. Ramesh, you mentioned the unsteady separation, but like you use a case like NACA 12 at 0 angle of attack. So I'm wondering why this is called unsteady separation? What's the T star used in your figures here?
So the T star is non-dimensional time over here. So this is actually a case which doesn't have any unsteady separation. So the cylinder case that I showed previously is a case where we have the unsteady separation, which, so here we have the C-sep indicator that's being exceeded because we do have separation in the case of a cylinder. But for the NACA 12 airfoil, the C-sep indicator is never exceeded because there's no flow separation over here. So this is just an example where there's no flow separation and where we are able to get a steady converged solution.
All right. So say it seems more like this is a steady case. So what's like say if T star changes, why your results changes?
So after T star equals 2, the result is not going to change because at that point we reach the converged steady results. But initially we start off from the inviscid solution where there's no boundary layer. So this is like we have an airfoil where there is no free stream and suddenly we switch on the free stream. So that's at time equals 0. So the boundary layer slowly develops and then we reach the steady solution. So that's what is happening here. So even a steady case, we are simulating it using an unsteady method. So eventually we get the steady solution after some time.
Yeah, thanks for the answer. So is anyone has any other questions?
Hello.
Yes.
Hello.
We can hear you.
Yes. Dr. Wang from University of Liverpool. So sorry. Sorry if I missed something. How would you treat reattachment using this method?
So we haven't yet got to that stage, but as I mentioned, what we are planning to do is we are planning to shed discrete vortices when the separation criteria happens. And for reattachment, what we'd be looking for is for this spike to come back down below the CSEP indicator here. So if reattachment occurs, then this spike in the displacement thickness must get shallowed out, and the CSEP indicator must come back down below the critical value. So this is something that we are planning to tackle in the next few years of this research.
Okay, so yes, I remember you did mention that in a previous talk of using the vortex using the free vortices to model the detachment. So one thing I'm curious about how you would go about is because the thing is the discrete vortex method, it's not a very high order method. So there is potential for some very nasty, how do you say it, numerical singularities on the surface tangential velocity once you have these shared vortex sheet either at separation point or beyond it. Do you think this vortex, which so strongly relies on your accurate computation of the boundary layer, would still work given now that you are in a separation region?
Yeah, I think that's a great point. So as you mentioned, it is very, very sensitive to numerical phenomena, and that is something that we've recently discovered. So for example, in the leading edge vortex modeling that I showed earlier, it's not very sensitive to the exact value of the LESP and so on, and we can use a high level of approximations over there, but we are seeing that really this viscous acid interaction and the boundary layer solution, these are quite sensitive, and everything needs to be done quite accurately and to second order in order to, to be able to get converged results and for the solvers not to blow up. So yeah, so we haven't yet gotten to the stage where we're able to fully do this separation and reattachment yet. But I am hoping that if things are done carefully and using second order methods, that we will be able to do it. But yeah, it is numerically challenging.
Thank you. It's very interesting. Would you mind me contacting you afterwards?
Oh, absolutely. Yeah, that'd be great. Mm-hmm.
Thank you.
So anyone has questions, you can just open your mic or you can left in the chat.
Hello.
Yes,
Hello.
we can hear you.
Hi. Good evening, Kiran. Yeah, I'm
Hi.
Yeah, I was a postdoc at Karen's group.
Oh yeah, good to see you.
Yeah, we used to meet. Yeah. I have a few questions. So first, you're using the integral boundary layer equation to predict the separation. Flow separation is proven to be very difficult to predict, and a number of factors that can affect the separation point. Like one is the transition. I noticed that you're doing at a very low Reynolds number. So does that equation can treat the phenomena like the transition, or?
Yeah. So that completely depends on the version of the unsteady boundary layer equations that are being used. So the ones that I'm showing over here are designed for laminar flows only. So with this, it's only possible to predict laminar flow separation. There are a number of implementations of integral boundary layer equations. So some of them are for laminar flows, some of them are for turbulent flows. So the ones that we are using here are for laminar flows. So if we go to Reynolds number 500,000 or higher, we'll need to use a different set of shape factors and so on that are designed for turbulent flows. And similarly, we also have some integral boundary layer equations that have transition models built into them. So that is something that we are planning to try in the future when we look at Reynolds numbers 100 to 200,000 and so on. So that totally depends on the boundary layer equations that are being used. So right now we've only tried this with laminar boundary layer equations. And in the future, we definitely do plan to try it for fully turbulent and for transitional flows.
Okay, I understand it's modularized. You can change the different sets of equations to treat that problem. Yeah. Okay, the second, I'm interested in your future work. You said the work is in progressing. You are predicting the beginning of this separation and not the exact separation process. So I guess that the separation on the surface from the trailing edge or in the middle of the cord would be much different from a separation from the leading edge. Just out of curiosity, how do you treat the separation angle? That's one factor I would be very interesting to discuss with you, because from the separation from the leading edge, it's more or less, I guess, following the incoming flow. And then from the, in the middle of the cord, then the direction, I guess it matters. It will influence the prediction results of the separation. Have you thought about that, or you have any ideas?
Our plan is basically to shed it tangential to the airfoil surface. There are already some discrete vortex methods in the literature for modeling separated flows from any arbitrary location on the airfoil. For example, there's one by Katz. That method basically assumes that the separation point is known, and then they shed discrete vortices, whereas we are trying to do it dynamically by first detecting it and then by shedding discrete vortices. So maybe I can explain it with a diagram. So for example, I showed the cylinder case, and basically we are predicting flow separation that happens like maybe at this location, like x by c equals 0.6. So this is where the displacement thickness on the airfoil becomes very sharp and the equations start blowing up. So we haven't yet done this, but the plan is basically to start shedding these discrete vortices as soon as that criterion is met. And what we are hoping is that once we start shedding these vortices and the effect of these vortices is accounted for, then we'll be able to get a converged solution in the viscous-invisible interaction. So right now it's possible to integrate the equations beyond the singularity, but we are hoping that if we start shedding these discrete vortices and account for the effect and account for the external flow, then we'll be able to integrate the equations even past this and be able to model the fully separated flow.
Okay, I guess the flow can evolve by itself into the a converged solution.
But like the previous question I mentioned, like it's numerically quite tricky to do this. So everything has to be done quite accurately, or the equations just blow up. Like there's very little room for error here, just because the equations are so stiff, like very close to that separation point.
Okay, I'm looking forward to see your results.
Yeah.
On that point, you said integrating beyond the separation point, but what normally happens is recirculation beyond separation. So what basically is your as boundary layer equation is normally a parabolic equation. So with the recirculation region, you really can't integrate in the forward direction beyond the separation point. You need to integrate from the rearward direction. Isn't that the case?
I think that would be for the steady boundary layer equations, which are typically parabolic equations, and we can't go beyond the zero skin friction point or the recirculation point. So this set of unsteady boundary layer equations are really a hyperbolic system of equations. And here we are able to go beyond the recirculation point already. So even in the NACA 12 at zero angle of attack, we do have reversed flow near the trailing edge of the airfoil. We don't have flow separation, which is the detachment of the boundary layer, but we do have recirculation region and zero skin friction over there. And that is something that we are able to model with this method.
Oh, I see. Okay. Okay, so since it's hyperbolic, you don't actually worry about which direction the information is traveling.
Right. We do have
Okay.
the, yeah. Mm-hmm.
All right. Thank you.
Okay, any other questions? If no, well, thanks again for Dr. Ramesh to give us an excellent talk here, and I will thanks for participating this IBM seminar. And that probably will be all for today. Thanks.
Thank you.
Yeah.
Bye.
Bye.